Askery. Right after, we have the cough break. And after the cough break, we have the poster section. So the poster section will be there, in the place we have the cough break. So you can hang your poster there, who is going to present. Okay? So the poster section is from 4:30 till 6. Tomorrow, you continue this poster section. Thank you.
It's working? Ah, it's working. So I see that you guys were working on this. This is yes. So probably we arrive at the same solution. The idea is that with this variational principle, you can estimate an upper bound for the ground state energy at least. So you have these ansatz, and this will give you a good approximation, an upper bound at least. So in this case, we should arrive at the exactly solution. So probably I see you guys did it here. It's not much. So you normalize, and then you find A like this. Now you have the energy, the potential plus kinetic energy. Then for the average value of the kinetic energy, you have this B parameter. And for the potential, you have this. Probably, I can see that, yeah, if I was about to see, yeah. So in the end, what you have to do, so you have the mean value for the energy, and then you have to differentiate in accordance to B, and then you have the solution. Putting B back there, then you find the exact solution. So for me, when I was doing this exercise, I realized that this is the main idea of KAOA. So you parameterize, and this will give you at least a good upper bound for the ground state energy. But in KAOA, more than that, the ground state is meaningful for you. So it encodes your solution. So here, in this example, the Gaussian gives you the best solution. So the take-home message is, Gaussian is a good trivial function. Because, well, even if it's not the true ground state, because, yeah, and if you are from physics, you already know that. It's easy to manipulate, so normalize and then to use as your function. And the variational principle, this is it's the very first example in chapter 8, I guess. David Griffith's Introduction to Quantum Mechanics is the part of applications of quantum mechanics. I think it's the very first example. So it will give you a good upper bound, as I said. And this is good for you to have in mind. If you don't know the exact solution, if you're about to guess a solution for something, guess the Gaussian. At this point in physics, you are very familiar with this guess. So I will give a brief and a schematically introduction on KAOA, Then I will go to the codes again and run the codes a little bit with you so that we see it working, right? So QAOA stands for Quantum Approximate Optimization Algorithm, or Quantum Alternating Operator Ansatz. It's a variational method, so this is why I gave you this exercise to get the feeling of what you were doing. It's hybrid, it's part quantity and part classical, and it's suitable for NISC device. That's a good point. Maybe not that scalable. Maybe you need to track a real problem. You still need a high number of qubits. Maybe not yet scalable, but it's suitable for the NISC device. So the main difference I would stress is that now you parameterize, and I will show you how you should parameterize the operator you want to minimize. In general, you want to minimize, it's a cost function. Then you want to minimize the cost function. But it can be the fidelity of the states, and in this case, you want to maximize. So it's changing your sign that will say that if you need to maximize or minimize. In this case, you are, let me go back. You are summing positive terms, so it's clear that you should minimize. There is no upper bound here, but sometimes you want to minimize or maximize. And the state carries information for you. If you look at the ground station, there will be a connection with your solution, right? So it's a hybrid because you parameterize and measure in a quantum device, but your parameters you update with classical algorithms. So in the code, I put some, and the best one is Kobila or Kobila. I don't know the right pronunciation, but I put many, and then I will show you. So in general, what you want? What's where the exponential appears? It's the connection I wanted to make. So you want to repeat this X structure many times. Is the profundity of your QAOA. So in the original paper, they claim that if with one repetition, you could get a good solution. That the claim they have in the paper. In practice, you have to put some layers. I think in the example, we use 5 layers, 5 repetition of this blue and red scheme. And in practice, you can try 5. It's kind of a hyperparameter. You have to guess by hand. So the gradient descent, if, for example, they will give you the best values for the parameters. But the size of the neural network, you have to guess. How many parameters? How many layers? So this is a hyperparameter. Everything that's outside the gradient descent to optimize, it's a hyperparameter. So then you have to guess by hand. It's a state of art or lucky anything that we can rely on. So, and what's the shape of these circuits? Is, for example, this shape or variations of these shapes. And in the end, what do you have? You have a parameterization, initial state that you parameterized, and now you use the algorithm to find the best solutions for you. So in the same sense that we did here, the variational principle. So I will go back to this tomorrow. This is because now I want to run the codes and show some things. But why it's suitable for the NISC area, how you can solve this, how do you write your function. Then we will discuss that more tomorrow. And we discuss also some reference. I mean, if you speak Portuguese, I invite you to read our tutorial. It's really well written, and Thaisa wrote most of this part of the paper, and then it's very well explained. Yeah. So if you speak Portuguese, check there, and tomorrow we revisit, okay? Any doubts, any questions so far?
That end that you explained in the last presentation is related to the dimension k of the amount of parameters. See, if you show me here, that for example, you say Q1, Q2 until Qn.
Yeah. And it's the Q in the
okay.
in the last one, because exactly. So let me go back to the code. I was just running before I came here, because if you are to run code live, it's very dangerous. It's like an experiment. Never say what will happen. Explain the experiment. So you do the experiment, and then you explain. If something goes wrong, you try to fool your audience. So I don't want to fool you. I just run the algorithm, and I fix everything that was random so that my answer will be right. Okay? But never try from scratch. So here I explain the whole idea, as I told you. What's an asset, what's a portfolio, what's a return, what's risk. As I said, it is in Portuguese, and I have no motivation to translate because I wrote a lot. So, but I think Portugal is more than enough. Those two here I will run. It's the two API, one for Niceplot and Yahoo Finance. This one, you can get your access, daily access. And I'm not sure if in Bitcoin you can try, in cryptocurrency, if they have more granularity. But I believe it's daily, okay? So let me just go back for the sake of completeness. I will tell you where to find it. It's in my GitHub. And this is this one. I tried this in English, but it's a very short version, but I don't guarantee it's working. So it's more or less the same idea, but less verbose. So, but if it doesn't work, come back here. This one, I have to make it work. So then I'm working this code. I was running it here. I will keep going here. So here you get some useful packages. Here I put just an example of Bitcoin, and I frozen the time phrase until 20 September 2001, because in the paper it was there, but you can change here and get more recent prices. Then you can plot. Here I'm plotting open, high, low, and close values for a given day. In my plots, it was just the close time, the close price, preço de fechamento. It was only the close price. Because for every stock, you get like four rows, like this. They have also this, adjust the close. It's more important for stocks. For example, if a stock pays dividends, they subtract the value of dividend after the close time. So for cryptos, this column is equal to the close, right? For stocks, it may vary a bit. So if you have any question, you can ask. Here it's I like this book API because you can make like interactive plots. You can zoom, for instance. You can check. Then I like this, but it's just for fancy plots. It's the same information as previous one. Here is where I decide the stocks. So for the sake of my talk, I will repeat because I know it's working, but you can try. You can put like, you can comment this one, and try just the American stocks, or you can comment this one, just try cryptos, right? And it also, I finished in the time we submitted the paper. It took more than 1 year for the referees to accept the paper. So I keep it freezing here, just you can read the paper and reproduce, but you can change the date here as you wish, get more data, and so on. Again, I'm just showing how you can get this data here. This is the fancy plot as well. And here it's a nice thing that when you do some papers, they take the log of the value. Log plus one, because the scale of the prices can differ a lot. When you take the log, they more or less converge to the same scale. And then you can see it here. So you see that this stock here fluctuates close to 0 in terms of the orders. So you take the log, make them more or less in the same scale. So it's a routinary practice. Then, so here I comment everything that I comment in the morning, what's portfolio optimization, what's the efficient frontier, and I'm just saying that our main goal is to reproduce this, and then how you compute the returns. And then here, let me show you, there is this fancy, the nice function that you just put like dot price change, and it does the trick for you. So you input your matrix of price, and then it will do for you. Of course, you have this non-value here, and I explain why, because you have this price change just for the second day one. For the first day you don't have, and I explain everything, then you throw out these. And then you plot the return, the daily return. So it's kind of noise. So I will stop here to say, if you are doing some predictions, if you want to play in the stock market and make a prediction, think, is this predictable? Should I waste my time trying to predict in this? Or is it just noise? It's a coin flip and I shouldn't try. So be conscient that it's almost a random noise, right? So be careful in trusting every prediction you can make. And then in here you can see that the dispersion of the blue curve is a bit higher than the dispersion of the orange curve. So it's an indication that the risk defined as volatility is higher for the blue one, right? So let's see. So I did this for all the assets I defined. Then I don't know why I'm repeating here. If it's too repetitive, just skip. Then I'm calculating the variance, the volatility. We make this, you compute it in daily base, and then you make like annual. And to make it annual, as I told you, you multiply by almost the number of days you have, trading days. For the crypto market, they never stop. Then you just use the number of days in the year. And then this will give us the ingredients we need. So I'm keep just running that to get to my point. So here we start with the portfolio risk management. Our goal is to arrive at that frontier, the efficient frontier. And here I'm just telling you that how we sample And I just want to show that you see the weights. Here it's a more or less uniform. I will run again. And sometimes, yeah, it deviates a lot of the uniform here. 6%, 6% of these, and most of the other stocks. So we use sample a lot to get that frontier curve. Then I explain again the Sharpe ratio. And now we are about to start. Let me just set in some parameters. So I put like 30,000 portfolios because it runs, I will let it run while I speak. It runs in about 2-3 minutes. Let's see. So far, you have any questions? So far? So what it is doing here, it's sampling that weights, computing the risk and the return, and stacking in a pandas data frame. So when I sample every one, it finished. No, it's still running. When it finished, I will have this pandas data frame, and then I can sort as I wish. Please give me the index of the portfolio with minimal risk. Please give me the index of the portfolio with maximal return, or whatever. So it finished. I'll have this. This is the data frame I told you. And here is how I plot this each out the frontier, but you can see clearly our frontier saying that given a risk, you have a maximal return. And give you a return, fix your return, and you have a minimal risk. It's not unlimited. For a given risk, you have a maximum return, right? So here it's just plotting how you get the portfolio with the minimal risk. I get the index, then the portfolio with maximum return, and the one associate with a given Sharpe ratio, and then here I will plot. So I will ask a question before you all sleep. How do you retrieve if I give you some points, how do you compute the frontier? How to do that? I give you, so far, I have by hand this example, this example, this example, this example. Yes, but the return in function of x is not a function. Because for the same x, you have many y's. It's not a function. So what would you do what would the trick? The trick is here. Let's see if someone could see. What would be the trick?
I'm quite out trying to follow you. Is this a quantum computer?
No, nothing quantum yet.
Nothing.
Yeah. Nothing quantum so far. It will be in the end.
And is this QAOA? The algorithm?
No, so far no. So far just classical. We sample an array of weights and compute those things completely classical. So the trick maybe you already got? Yeah, x in function of y is a function. Not y in function of x. It's just in the polynomial fit, I said that I inverted it here because I'm saying that I'm trying to find x in function of y. Just that, because it's a function. And the degree 2. And then you plot. So you see that it's a function in the inverted axis. Okay? So this is an important trick that I have to tell you, is that this code only runs with Qiskit this specific version, or lower, not higher. Because now we are going to enter on quantum. This is, we have this Aqua package, or Aqua branch in Qiskit, that has a very friendly interface for quantum finance. So basically you say, solve QUA with any qubits, with any layers, please solve for me. I don't want to tell more than that. So this Aqua has this nice package. It's the one I'm using here, and it's deprecated now. So for new versions of Qiskit, it doesn't work. Only this is the last one that it works. So you have to install this specific version. So my code was not running before I arrived here. I was a bit desperate, and I said, okay, it has to run because I have to show, and then I have to see the documentation, and now at least it runs. And then, as I told you, it uses some optimizers. You can play a bit with them. I will show only this one, Kobila or Kobila, but you have this square list, quadratic, stochastic, quadratic, polynomial. I don't know the acronyms for all of them. You can play with them. And now we discuss a bit the problem in terms of a quantum approach. I told you that I'm making a nice comparison with soccer. In some sense, tomorrow I have a picture. You're about to start a game where you have to pre-select your stocks. From the morning, you should have an idea why you should pre-select. You have to avoid the over-precified stocks and things like that. From the whole pool, you need to take just some few, like the coaches. They have to bring 26 players. So when you do portfolio management, you don't want to change your approach all the time. You have a few substitutions to make. So you want your initial squad to play well in almost the scenarios, almost all the scenarios, defensively, aggressively. So if you look at the distribution of what the future can bring, it should play well in all the situations. So this is not my idea. It's Howard Marks' idea. The book I showed, the book name is The Most Important Thing for the Investors. And how he compares with the soccer. Because now in the quantum scenario, we have 4 variables, x1, x2, x3, x4, related to those stocks. And my idea is, which one optimizes for me? Optimizes what? It minimizes a cost. And how I define a cost? Or how I define my cost function. So you define your cost function. So now I apologize with you guys, because this sigma here is the big sigma there that I showed you in the morning. Is the correlations, how are they correlated? And here, again, it's the return, and x is this binary variable that I can include or not. And as I told you, the budget now is a bit different. It's how many stocks I should include. In this case, we run the code saying that, okay, you have to select 2. And every time it's more than 2, I put like a penalization. This term is somewhat a constraint, or you can see it as a penalization. I don't want more than 2. So the number of stocks minus B is optimized when the number is 2. So to do this, you can include a term like this. What you are saying here is that you put the square root so that it's positive, and you say that if it's different from 2, the number of stocks, penalize. The only case is not penalized is n equal 2. So it's this kind of thing that you want the computer to solve. So in combinatorial optimization, we could think that you are running all the cases and take the one with the lowest cost energy that you can define with in this sense. Okay? So what we are going to do from now on is that it's in the same notebook. I'll take the same array of returns and the same array of covariance and putting it in the quantum and test. Okay? So I did many approaches. So I'm just using the values before. And what I'm doing here, as I told you, this code is not a full implementation of KUA. If you want the full implementation of KUA, it's in the other notebook of this project. There we have a full implementation of KUA, completely made by hand, and only for the KLM simulator. Because as I told you, the idea, we have a marketing idea that was showing that we could do everything with which was in Brazil. So we did this for KLM. It's not a famous simulator in terms of in comparison with Qiskit or Perlin or so on, but it has a nice interface as well. Here it's very simple. I say I have a number of assets, 4. I have, of course, a number of qubits, 4. How many layers I want? I want 8 layers. Repeat that KAOA architecture 8 times, right? And then I'm just saying that putting some values for this. And Q here, I didn't tell you, but it's a calibration of risk appetite that you want. So if you put it higher, you're saying that, oh, I'm looking for higher values, and then I want to get that value with the same risk, I have to be more aggressive. So you can set any value you want. Here I set 0.5. The number of assets is 2. And that L here, in fact, I made a lot of confusions, but it's this alpha. Sorry. It's just a regularization term. But it's not going to play a fundamental role, because anytime that the number of assets deviates from B, which is 2, then you have positive something. It only changes the scales in the minimal energy. But you probably arrive at the same energy. So let me go more. So it's just nice fancies. Oh, directly from NumPy, you can solve this problem. And then I'll show just the solution here. It's not quantum so far. So it's a classical solution. They have also this optimization in NumPy. Then here, it gave us the solution as we imagined. So let me go back here a bit. Do you remember that No, I have to go back. Let me go to the maybe here I have this. So, we are testing those scenarios here. In our case, we are testing specifically this one. So, what we were expecting is this. The classical solution is this. Most of my stocks, 40% of my money in this stock and the rest in this stock, this is almost zero. So the kind of ground state that I was looking is 1, 0, 0, 1, right? This stock, not this stock, not this stock, and this stock, right? So now I can go back and see what the solution we get. So now, KAOA, here I'm using the optimizer, that one, Kobila or Kobila. I never know the name, the pronunciation. And with 20 layers, and then I try to find the best solution up to 25 interactions. So, yeah, it's okay so far? So let's see. So the output is this. The minimum energy is for this state. So we are good so far. And then the associated probability is this one. So in this case, I think we can say we have a solution because the probability of the most likely state is more than double the second one. Sometimes you find those three best one with close energy and close probability. So here I would say we kind of solved the problem. And we tried also the VQE. So what I'm showing you is that with this Aqua API from Qiskit, it's very simple. We almost did any code and tried two quantum algorithms. And here I put a seed that I know that we get the right solution. I would say that we also have found a solution because the probability of the ground state to be this is much higher than the second one, the second best one. But now I know how my code gets wrong because I know him well. I will put a seed that probably won't converge to the best solution. Let me see if he will, yeah, see? I just changed the random initiation of this parameterized the circuit, and it couldn't converge. So let's just play. Let me try someone. The one who was working, I have to copy it here before I forget. And then the code is useless. Yes, let's try again. I will do the same with KAOA, just in case, and let's change the, now it's a very good solution. But yes, it's a very good solution. But it's kind of, you see, it's very tricky because it's really random in some sense.
If you made the simulation with many seeds and took an average, would that help somehow?
Yes. In general, I mean, in the final answer, we did just that. In the final answer, we just did that. We make an implementation with many averages. So let us do this with KUA, because let me save the one who is working, just in case. And let's see. And you guys can play with many other variables, the optimizers and so on. Let's see KUA, it worked, it even improved our solution. So, we didn't compare the problem fairly. It's not the same problem. Because in the first case, we had like a real number, which is the weight of that stock in your portfolio. Here, we are asking just, can I put or not the stock? We can do this. We tried, but it didn't work because it doesn't scale. You can make, it's an idea. I'm not angry if you steal the idea and publish that. And in fact, I really motivate, is that you can represent that partial fraction by a binary representation. You see? So you cannot not have one qubit per stock, but you can have many qubits per stock. And then you can make this, retrieve this to the fraction. For instance, we can have a binary representation that, for example, for the first stock, for the first one, you can have this. Just the first one, right? And then this string can be translated in the fraction. How can you do that? This can be that, should I put like 0.1? Should I put 0.2? Should I put 0.3 or 0.4? I mean, in the first decimal. And then if you want like 0.6, for instance, can be this and this. 0, 1, 0, 1. It turns out to be a 0.6 fraction of the first stock. So you see, to put like the centesimals, you have to double the number of qubits. So we tried a very easy implementation, but it didn't work. I think it's a good idea to publish and compare like the classical approach with the quantum approach. So you have some normalization problems that these guys have to, or this is for the first stock, now you have 4 bits. And for the second stocks, you have 4 more bits, and so on, but they have to normalize. I mean, we tried a very simple implementation and it didn't work. And we stress that is similar problem, related problem. We are feeding the quantum and the classical with the same data, but it's not exactly the same answer we are giving. So we were very honest with this description. I don't know more. Here is a long explanation of the simulator. And here you can find the implementation that I will discuss tomorrow. And I will let you guys with an exercise that take this implementation and convert that in the language you want, Penileni, KUA. And here we show that we set up the problem and blah, 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 and blah, blah, blah. But let's go easy. Let's let it for tomorrow. So tomorrow we have this overdose of KUA. Today, I'd like to show the code running. And I hope you can try with any assets you want. So I let times for any question if you guys have. And for the moment, I will let it running with this. I will run all. You can easily run all like this. and let it run all at once. So while I'm talking, I will see what frontier it can take from those stocks. Facebook, Amazon, Netflix, and Google. So for the moment, if you have any questions. Oops. It's never good to show it online. Let me reset. I hope. If it doesn't hope, I give up. So. Questions? Yeah.
For me, it's interesting that the web form of the optimal function. There is no analytical expression to that.
I think that for this case, those restrictions we implied, you can do analytical with Lagrange's multipliers. I think we can have an analytic solution for that.
So, I mean, instead of doing that polyfit that you do in order to find the optimal in the first example, so you say that there is an.
Yes, there is.
And the other question is that the function that you describe, the risk in the first example, compared with the QOAL, is different, right? Because in the first you calculate the volatility and the root square of multiplication of the W and the covariance, and in the other you add a Q, parameter Q that express the risk. So I think that I don't know how to compare both models.
Maybe the definition is a bit different, but we are feeding exactly the same returns and covariance. Maybe it can vary in terms of absolute value. Maybe they differ for half, but it's essentially the same. If you put Q equal 1, it's absolutely the same. Because the other things are exactly the same. I just follow the code, and then from here to there, use the same input.
And the x dot, the covariance dot, the x is always positive, right?
Yes.
And is there some difference if the constraint that you put to fit the number of portfolio that you press, to put it in absolute square instead of square, because that you are putting a lot of weight in that constraint.
You mean where do you mean exactly?
The constraint that you put with a b. Put a b. So for me, it's like when you do it with the square, you are putting a lot of weight in the minimization.
You need the square so that it's positive and it try to minimize. You need even.
Square, but instead of that, you put an absolute square of that.
The problem is it's not differentiable. So maybe the optimizer find it.
But I think it's numerically. I say that.
Yeah. The problem is people put the square, not the absolutely, just to that. When you try to optimize, it's easier to differentiate. But essentially, it's the same idea with some positive terms. You can put 4, 6, 8. It must be a.
It makes sense because the first term is R of x to the square. So
Another question.
I have a question. At the end, you showed that you want to find the optimal bit stream to minimize the problem, but you want to that bit stream means okay, I want to invest in this asset or no. But you say that use some quantum algorithm. So my question is that minimum function that you want to find map it, I don't know, to a spin model or something like that. Try to minimize that. They run the state, or you only expect a quantum algorithm to minimize that classical function.
Yeah, it's exactly. There is a nice paper converting every Ising model in kind of this model and vice versa. I forgot the name of the author. But it is very famous paper that they put, it's more or less.
The
Yeah.
position, but only just one string. So it's like has any relevance to map these kind of problems to a easy type model or something like that? No.
The only problem here is if the problem is degenerate, that you have the same different state with the same energy. But it's not the kind of things that you find in this kind of Hamiltonian. So, because you see that I print the probability and the energy for all the state, then you can see if you have any problem, like if degeneracies or something like that. But it's I mean, when I say it's not, suppose that you have all the Ibovespa stocks. So this problem is so big. So SP 500 in US. So I'm doing with 4 stocks here. So it's not that scalable. You can see that you cannot fit this in the circuit model, right? You cannot fit this in a Qiskit in our IBM computer. See? So it's hard to scale this problem. And people, I mean, big money people, they want to see, they will ask you that, do this with all the stocks in Brazil. They will not give you trivial questions. Because if they are putting money, they would like to scale up, say, this 100 stock or 200 stocks. So this is a proof of concept so far, in my opinion. Oh, it didn't work, and I don't know why. Maybe I did some mistake here.
But in KOA, how does the number of qubits scale with the number of stocks?
I think this is a trick question. Yeah. It's any. In this problem that we are, in this problem, no, but in the problem that we are saying, it's any. The number of assets. But it has to be with the architecture of the system and blah, blah, blah. How can they implement the gates that is involved? But, I mean, in the logical, it's any. You need any qubits, 1 per stock.
100 stocks? 100, around 100 qubits should be enough?
Yeah, it's doable. But people, in this kind of portfolio optimization, people use D-Wave. I think it's ahead of everybody because they have more qubits. And then, for instance, companies like Multiverse, and I think is the name, the best, at least the most famous startup working on this, they claim that they can do this for all the stocks in US market very fast, and can plug this with your Excel and something. Is the way that they are selling, and they are a big name in this portfolio optimization nowadays. So in our case, it's a demonstration of KOA implemented with circuits. More questions? Yeah?
A little bit off topic. We use Yahoo as the data source. Yahoo is not very precise for considering stocks, they take into account splits and dividends and so on. Is there a good data source you recommend for use the Bovespa in the Brazilian market?
To be honest, let me just comment here because it's not working. Then you exercise to see why it's not working. Maybe some step before. Let me. It's a good question. Until last year, it was for free. It was so good, Bovespa. It's all data for free. Tick data for free. Now they charge you. And I was tracking. I used to download every month. I download all the data. So I stopped for 3 months of tracking. And now it's not for free and expensive. So I think that you can test this. You can do exercise as well. And if you are interested, you can see the same noise in the crypto market. The data from Binance and KuCoin and any other Yahoo Finance, they are different. They are noisy from each other, if you look in this perspective. I don't know how large would be this difference, but Yahoo is the best one for free, I know, for the Brazilian stock market. It's the best. There is a Google has an API also. I think I wrote it here. Google has an API, but it's now deprecated. There was a bunch of APIs, but they stopped giving this for free. I think Yahoo is one of the last. More questions? Yeah, so.
Thank you again. Now we have time for the exercise. And later at 4, we have the coffee break. And 4:30, this poster section. Thank you.
Eu tô vendo aqui os exercícios que eu pensei. Cuidado aí, só.
O pessoal está pedindo os slides, que tem uns exercícios para eles fazerem.
Ah, beleza. Eu entrego para o rapaz ali, né?
Manda para ele.
Pronto.
Aí ele posta no
Tem a
site.
solução também.
Oi?
Eu já vi que tem a solução também.
É, tem a solução.